Right? The first section is going to be looking at primarily the unique behaviors and properties of water, because really wherever we look on this planet and we find a little bit of water, no matter how minuscule, we find life. Right? So we have to start fundamentally with what we understand to be true about water. Water has several unique properties about it, and one of the most curious properties about it, in my opinion, is how it behaves at different temperatures. Now, what's interesting about water is, in the liquid state, I could stir that, but I don't necessarily have to. Why might that be? Why am I okay to just put some of this food coloring in there, and I really don't need to stir it? In fact, if I'm this patient, probably within the next 5 minutes or so, it's going to be rather uniform in color. Yes, sir? Because the molecules are still moving around. Absolutely correct. So when we're in the liquid state of water, right, it's liquid because the molecule is able to do what? And what makes the liquid state, I guess, special, or different or unique compared to solid or gas state? It's an idea. Takes the shape of the container it's placed in, absolutely. And then what else? There's one other important thing. And I'll say that Gabby and Hannah, right? Yeah. Use this property of liquids. Yes, ma'am?
They're heavier than gas molecules, so they don't just fly off.
I'm going to carefully disagree that a molecule of water is a molecule of water no matter whether it's in solid liquid or gas state, and that a molecule of water has exactly the same mass, whether it's solid liquid or gas state. However, I think I know what you actually mean when you say that. Can you maybe help?
The density?
Okay, what about the density of it?
It's not as dense as the gas, but it's not as dense as the solid, but dense as the gas.
You're right in saying that there's a difference in the density of solid versus liquid versus gaseous water. That is true. I don't know if we can agree with the comparison in terms of which is most dense and which is least dense, but we'll get to that. That's not the other property of a liquid that I'm looking for. No? Go ahead, Nathan.
Molecules are more move around than solid, but less room to move around than gas. So it's just kind of
Right. Okay, so you're saying that at a higher temperature, the molecules are more spread out. Okay, so that they're not as close together as they are when they are liquid, and and then when they're in a solid state, if we have ice, then the molecules are even closer together yet. We agree. Okay, all right, but I still haven't heard that other property that liquids have that solids solids do, but gases would not. Yes, sir. Maybe not so much uniform volume, but the fact that they have a specific volume, yes. That you can that they have a consistent volume, yes. Remember, liquids they do not have a defined shape because they can take the shape of the container and put them in, but they do have a definite volume for sure. And that allows us to measure. Getting to measure and having to measure 1,000 milliliters wasn't 1,000 milliliters. If that wasn't the case, then we wouldn't be able to measure it. That's different than gases. Gases have no defined shape and no defined volume. Right? They can spread and take out whatever space, take up the space that we provide them, regardless of how much that or how little that is. Let's see, what else? Oh, all right. So there's some left. Oh, very little. But there's some that can survive. Yeah, solid water. Oh, well, I don't know. It floats. So what does that mean about compared to water?
Less dense.
Less dense than water. Okay, so for me, that is a very interesting property that water has that we don't see happen with many other substances. The fact that it in fact becomes less dense when it's frozen, when it's a solid state. Right? The question is, why? Right? We all, I think this is not a situation that we're unfamiliar with. We want a glass of ice water, we throw some ice in some water, boom, you have a nice little cool drink. But and we know that when we put the ice in there, it's going to float. Because the ice itself, as we mentioned, is less dense than the liquid water. But fundamentally, like why? Why is the solid state of water less dense than the liquid state? If you recall that the density is found in grams per milliliter, that is really telling you the formula for density. That density is equal to, well, what do we have on top in our units? Grams, which is a measurement of
Weight.
not weight.
Mass.
Mass, yes. Okay, and then we have it divided by or over volume. There, you got it, right? This is easy. Right, so density is mass over volume. But if you don't remember the formula, remember the units it's measured in, you can backtrack into math. What does it mean to be an intensive property of matter? This is intensive. Yeah, so an intensive property does not change regardless of how much you have. So yeah, you're very, very close. No matter how much you have, no matter if I have this much water or like 10,000 gallons of water, the density of pure water is always 1 gram per milliliter. Always, no matter what. In the ocean, in the lake, wherever. If it's pure water, that's its density. Right? Pure water is the key. The extensive properties will change based on how much I have. If I have more water, then obviously there's more mass. If I have more water, then it's going to have a larger volume. But it's still like yellow water. It's still going to be a color yellow. So it doesn't matter how much or how little I have. It's still yellow water. Another idea, I suppose, could be like connectivity. Like if you use copper wire, it has a certain connectivity about it. That doesn't matter like how little or how much copper you have. It's the conductive material. Right? It's intensive, no matter how much or how little you have. Okay, so that's kind of a wow. That's like a review of some stuff you should have come across like 7th, 8th grade. Hopefully. Okay, so but that's still not like explaining helping us explain why ice will float on top of water. In order for us to understand that, we need to also be able to pull forward from previous thought, like the differences between different compounds, like how they're put together. So, for example, or for I guess we'll just answer the question. Like we should all know the chemical formula for water.
H2O.
H2O.
I was right.
All right, we should know this. Whether you know it from like watching the water boy or or science class, you should know this. Right now, what does this formula tell us about water and what it's made of? There are 2 hydrogens and 1 oxygen. Yes. Right? You should be able to look at this formula and recognize that this number that is subscripted is telling you a note about the previous element. Right? That this is talking about the hydrogen, not the oxygen.
Ooh, I'm on the break.
It's also telling you that they're all bonded together. Right? If you had a coefficient in front, like a big fat number 2, this is telling us that there are 2 of this entire water molecule. There are 2 of them hanging out. Right? We understand that. We're okay with that. Okay. That helps, right, for us to have that idea in place. The second thing we need to know or be aware of is that obviously this is a compound because we have more than one element chemically bonded. Right? Now the question is, what type of compound is it? There are 2 major types of compounds.
That's mixture. That's mixture.
That's a mixture. Well, that would be a solution, actually.
Yeah. Yeah.
So, what type of compound is this? Do you recall the 2 different types?
Give me like 10 years.
The two different types of compounds depend upon what they do with their electrons. It involves the valence electrons, for sure. But that's one of them. What's the other type? You have covalent compounds and you have ionic compounds. Yes.
Yeah, we win.
Why didn't you say it?
We win.
Okay, so
I told you to.
okay, so a step in the right direction. Then we need to know, like, when you look at a chemical formula, how do you know whether it's ionic or covalent? There's an easy way to tell. Dom.
One of them is like if it's all metal, right? Or is it all the same like type of element? I'm confused.
You had me with metal, but then
Oh, yes, okay.
yeah.
So like, is ionic the one that's metal? Like that it has to be this both have to be metal to bond?
No.
Well,
You're
where's that
halfway
on
there.
track?
Yes, Rose. Yes, you got it. Winner, winner, chicken dinner. Yeah, right. If you have a metal element with a non-metal element, the compound is ionic. Because the non-metals are greedy for electrons. They want to steal them. Right? And the metals really have they're really indifferent to getting the electrons taken from them. Can you name a simple ionic compound?
Wait, 10. No, that's an element.
You put it on your fries like Paul does.
NaCl.
NaCl. Yeah, sodium chloride. Yep.
Brass.
Alright, so NaCl, a simple ionic compound. Now, what you also need to understand is the process that happens in order for these to become and form into an ionic compound. You should know this from before. Right? So if I wanted to know, like, how many protons sodium has, where do I look?
Right
How do I
there.
know?
Right there.
Okay, what do I look for?
You look at the columns for the valence electrons.
Well, that's where you're going to have a talk. I want to know the number of protons.
Oh, protons. Hold on. You subtract the. Dang it.
I know this again.
Protons.
Oh, is it the number?
The protons are equal to
Yeah, the atomic number.
Yes. Yes. It's the atomic number in the top right-hand corner. It's the whole number that's inside the box. Right? It tells you that the atomic number is equal to the number of protons because it's the protons that determine the identity of the element. Right? Like sodium is sodium because it has 11 protons. If it has 12 protons, it's magnesium, not sodium. Alright, so there are 11 protons. Alright, so 11, we'll have P plus, there's 11. If sodium is neutral, what does that mean about the number of electrons? Yes?
Same.
It's the same. It's got to be the same. Absolutely correct. Okay, no problem. So electrons, there are 11. For chlorine, how many protons do we have here?
Well, ring. 17.
And how many electrons if it's neutral? 17, all day long. Okay, now we get into the idea of valence. Right?
If it's not
You should
neutral, it
recall
explodes.
that the electrons are housed in energy levels starting closest to the nucleus and working away out. We would recall that.
Valence.
What's the rule for the number that can fit in the first level closest to the nucleus? Yeah, 2. Max is at 2. And then beyond that, it's what? For each level after. For right now.
2.
Keep it simple.
Isn't it 2 after?
Nope.
2, 8.
Nope, not 4.
8.
It's 8 of them, yes. Alright, so
I knew it was 8 somewhere.
keep that in mind then when we're looking at, when we're considering the electrons around these guys.
14.
Alright, so we have sodium within its first level. We put 2 electrons in there. We go to its second level, and only 8 more can fit in there. So we put 8 electrons in. And now we go to the third level, and we have 1 more electron to place. Okay, so we're just using numbers. I know probably some of you have seen this, and you're like, oh, we put dots in there. Right? We're just using numbers. Just kind of make it short and easy. Right, so, and you're right. If we look at what group sodium is in, It's in group 1, which tells us it has one outermost electron. So we agree. So I can actually simplify this whole thing. Let's erase the whole thing here. Sure.
It's just
And we'll say Na, and we'll put a single dot on it. Right? This is a Lewis dot diagram for sodium. It shows you how many outermost dots you have. Right? One valence electron. We're going to do the same thing with chlorine. Right? Energy level 1 gets 2 electrons. Energy level 2 gets 8 of them. And then energy level 3, we said the remain has to go in there because we can go up to at least 8. I love it. At least. Okay, so now chlorine has how many outermost electrons? 7. It's in group 17. It's the 1's position in your main group elements. Right? Groups 1, 2, 13 through 18.
So that's why it bonds.
The 1's position tells you how many valence.
I see.
And that's what drives chemical stability or chemical reactions. It's trying to complete that set of electrons on the outermost level. For most elements, it's going to be octet. It's going to be 8 we're looking for. Hydrogen and helium are different because they only need 2 to max out energy level 1. Okay, so we can also simplify this one down, showing just the outermost electrons.
Yeah.
Right, so we'll write Cl for chlorine, and we'll put it's 1, 2, 3, 4, 5, 6, and because I want to, the last one will be here. So, chlorine is electron greedy. Sodium really could care less. Sodium would like to give up that one outermost electron. Chlorine wants to gain one more because it's easier to pick one up than give 7 away. Okay? Matter is lazy. Right? So it goes through this process. It does this. Chlorine will steal the electron from sodium. Sodium gets what charge when it loses one electron? Brendan?
I wish I could see like that.
No. It's going to keep the same number of protons, but it's going to have one fewer electron, which will give it a positive charge. Right? It's still going to have, right? It's still going to have 11 protons, but now we've removed one of the electrons. It has 10 now. Chlorine is going to get what charge? It's going to be a negative charge because it's going to pick up that one more electron that it stole from sodium. Right, now, this is what makes it ionic. The opposite charges do what? They attract. That's like two opposite magnets. Boom, they're stuck together. We have the ionic compound, sodium chloride. Okay, so that works well for, again, sodium and chlorine, making sodium chloride. We also mentioned, we said that if you have a nonmetal with a nonmetal, it's covalent. So is water ionic or covalent? Covalent. Yes. It's a nonmetal bonded with another nonmetal element. And there's a lot of side conversations going on, but just saying, like, if you don't know this, you should. And if you don't, and this is a mystery to you, you should be writing stuff down. If you're not, then that's on you. All right. So this is a covalent compound, nonmetal with nonmetal. And so, how many outermost electrons does hydrogen have? It's in group 1, so it has 1. You got it. So we can sketch this down with this little dot diagram with a single dot over it. Right? We're going to put this with oxygen, right? And oxygen should have how many outermost valence electrons? 6, because it's in group 16. Yeah. Yeah. Use the 1's position of that.
That's why there's 2 hydrogen. It's 2.
You got it. Yeah. So you're already kind of seeing the writing on the wall here, or the writing on the panel. Right? We recognize that there is a space here and a space here for another electron to satisfy oxygen's need to have a complete set of 8 on the outside. And oxygen is more greedy than hydrogen is. They both want electrons, but oxygen's a little more greedy for them. And so they will coordinate and share electrons. Right? We will see that happen, where these 2 electrons, or this electron right here, these 2 will actually be shared, and we'll represent that by a single bond line between each of those atoms. Right? So this line here, this bond line, is representing 2 electrons, and there are 2 electrons here too. If you consider, like in a moment of time, if all these are shared back to oxygen, it has 2, 4, 6, 8. It has everything it needs. If they're shared back the other way to hydrogen, it has the 2 that it wants, or the 2 that it wants. So this works well. Now here's where we might have a little bit of a problem, right? As far as water goes, right, it's actually a bent molecule. It actually looks like, and smells like, and tastes like
Water.
like nothing. But it looks like this, right? And so, whoops, maybe we need to move it ahead a little bit. There you go. Right, looks like that. Okay, so our sketch does not show that. Right? And so we need to maybe dig a little bit deeper into what's going on with the structure of this molecule. So this is the note handout for this unit. I'll get it to you so you have it. Right, and once they move back there, then we'll shift it up, the extras up to the front.
Okay. Could we make our own compounds?
What's that? Why? I made mine on compound 39.
Now, what we have to consider is how these elements are actually being put together for this covalent compound. They're sharing electrons between the atoms that are being bonded. And if they're sharing electrons, all of those electrons are negatively charged. Right? Wait, I didn't want to show this.
Hey, sucker.
It's destroying the environment. That's really
So if this is how water looks, then why, when we structure it using using a Lewis dot diagram, let's find a thing. It looks linear, it looks symmetrical, it doesn't have that bent shape. And the reason is we have to consider that this molecule is actually going to exist in 3 dimensions, not flat on a page.
Yeah.
Right? So if we consider that idea that these electrons will not want to be right next to each other as they're being shared, and it's going to look something like we had 4 atoms bonded to a central atom like carbon with 4 hydrogens bonded. Right? It's going to look something like this. Right? And the reason is they all need to space themselves out in equal directions in 3 dimensions of space. Now, the other question would be, well, wait a minute. Water only has 2 bonded atoms. This has 4 bonded atoms. So why does water become bent? Or why is it a bent-shaped molecule? If we remove these attached atoms, right, and these represent then the electrons that oxygen kind of hangs on to around it, those 2 pairs above and below oxygen, right? There's your water molecule, your bent-shaped water molecule. Because you have this negative region around the oxygen atom that's pushing the hydrogen up and away to be bent like this. Right? It's this bent molecule shape that really gives way to all the other properties we see water to have, that makes water unique. Right? Tomorrow, when you come back in, we're going to look at those properties, and then also use some lab investigating, exploiting the properties of water. Things. And we mentioned the last time we were together discussing some content that the water molecule, it is a molecule because it is a covalent molecule. And so we should be able to answer and respond to questions as to like what makes it covalent, why is it covalent, and also like why do we always draw this water molecule like in this way where it looks like, you know, it looks almost maybe bent in its shape, or that these hydrogens are kind of snuggling up close to one another on one side of the oxygen atom. Right? So we should be able to answer these questions, and that's why we're going to kind of review some stuff here today. right, so ionic compounds then, they're going to look at gaining and losing electrons. They're going to be stealing, taking, and something along that lines as far as electrons in the valence level of the atoms involved with the formation of the compound. Right? And the key here is that they want to complete their outermost energy levels, also known as their valence level. Sometimes some books and instructors will refer to them as shells. I usually refer to them as levels, just because I kind of grew up with level 1-1, level 1-2, level 1-3. So I kind of carry that forward. I think when I consider the energy levels that we place electrons in. Right? And we should also know from prior knowledge that these atoms are going to be the most stable chemically when the outermost valence level is full, with either 2 for level 1 or 8 electrons for anything beyond that. Right? So that should be something that we're familiar with. So again, the idea, if we were to sketch out the electron arrangements of some simple elements on the periodic table, you should be knowledgeable enough to understand that on the periodic table, the atomic number is equal to the number of what in every atom? Yeah. Protons. Number of protons, always, yeah. So we'll stick with simple stuff, like we'll choose sodium out of here, because sodium is a very common metal to be found in compounds. Right? And so if we consider sodium, then if we were to sketch out where its electrons are at, and actually, you know what? I'm going to hop this out of here, and we're going to go into this. We'll just sketch some stuff up. All right, so if we consider sodium, right, it has, as you mentioned, its atomic number is 11, so that means in terms of protons, it has 11 of them. Neutrons have no charge. They're found in the nucleus, but they really contribute to the overall mass of the atom. If we want to know the number of neutrons, we need to know the number of protons and the mass number of that atom. Now, the periodic table does not give you mass numbers, but if you round the atomic mass number on the periodic table to the nearest whole, that would be the most common mass number for sodium. So, and sodium has like 22.9898, so we would round it to the whole number of 23, and so 23 minus 11 would tell us that there are 12 neutrons in the most common forms of sodium. For the electrons, then, if it's neutral, they have to be equal to protons. Yeah, so simple stuff. This should all be coming back pretty quick. All right, so if we wanted to draw a model, a diagram showing where these electrons are placed, again, we're going to keep things simple and say, like, from prior knowledge, level 1 can only hold 2 electrons. Level 2 and up can hold up to 8 electrons. Then we would fill in sodium as such. Like let's get rid of these numbers here to give us a little bit of room with our diagram. And we'll switch there. All right, so this would be level 1, this could be level 2, and we're going to need level 3. And we would consider that as far as electrons go, right, we'd have electron 1 and 2 in the first energy level, and that's full. We can't put any more in level 1. So we now put the next 8 in level 2. So 1, 2, 3, 4, 5, 6, and 7 and 8. And then finally, we've used 10 electrons so far. There's 1 left. And I can't put any more in level 2, so it must move into level 3. And there's my 1 outermost valence electron for sodium. Now, there are a few cheat ways to know if your element has 1, 2, 3, or 8, up to 8 valence electrons around it. And that is to simply look at what group number it's under. For groups 1 and 2, and 13 through 18, the vertical columns of the periodic table, right, you can use the 1's position number to tell you how many valence they have. So all the elements in group 1 have 1 valence, just like sodium does. And all the elements in group 2 have 2 valence. This is a region that we have to skip over a little bit because in terms of how electrons are placed, there's more to the story than what we're telling you right now, but it's not really pertinent to what we need to cover. And then from groups 13 through 18, the trend picks back up, where in group 13 you have 3 valence, 14 have 4, 15 have 5, 16 have 6, and you get the idea. All Right, so if we were to also consider like maybe not a metal like sodium, but maybe a non-metal like chlorine, right, and we were to sketch that guy out, we'll do the same thing in red, so Cl for chlorine, and we were to, again, do like a model for its electrons that are placed around it. Notice that I already know for chlorine I need to use 3 levels in my model, and I know that because the period that the element is found in gives away the highest level that I put electrons in. So just like with sodium, I was putting electrons in level 3. For chlorine, with its 17 protons, to be neutral, it has 17 electrons as well. The first 2 go in level 1. The next 8 go in level 2. So we'll sketch those guys in. And this takes probably the most amount of time, is just drawing these darn dots. And then we'll get the 1, 2, 3, 4, 5, 6. I'll put my 7th dot over here all by itself. All right, so if the name of the game for these guys in terms of chemical stability is to fill or have a full outermost valence level with 8 electrons in it, remember that matter is lazy. Right? It's only going to do as much as it needs to do to be stable, and that's it. So for sodium, is it easier for sodium to find 7 more electrons or give this one up?
Give one.
Yeah, just give one up. It's easy. It's easier. It's less effort. Does someone take this from me, please? Right? So sodium does not just do this on its own. It's not like where sodium is hanging out there by itself and says, "Here, there, someone take it." Right? Something has to actively remove it from it. And that's what's going to happen with chlorine. So if we look at chlorine's outermost valence electrons, it needs just 1 more, and it's complete. Right? If you want to maybe use a periodic table to help you out with this, it's every element wants to be a noble gas. Every element wants to be that noble gas. And so what is the shortest route to get back to the noble gases? For sodium, it's to lose 1 electron and be like neon. For chlorine, it's to pick 1 up and be like argon, if it can. All right, so when these guys get close, chlorine's going to say, dude, I can really use this. Thanks. We're going to take this guy and move it over, and I'm going to use it. And when it fills in, then, now chlorine has a complete outer valence set, right? And sodium, with the removal of this, with the removal of this, there's nothing in this outermost level, right? So it's almost like this level doesn't even exist anymore around sodium, and so now it's complete. So now chemically they're good, but now what is different about them? What's the major change and from what they were just a little bit ago before the electron got moved? Go ahead, Jeff.
They aren't neutral anymore.
Why not?
Because sodium lost an electron, so now it has more protons than electrons, and then chlorine would have gained an electron, so it would have more electrons than protons.
Yeah, the proton count does not change, right? Because if it does, we change what it is, because protons dictate the identity of the element, right? Anytime we have an atom with 11 protons, it's sodium, no matter what else is with it. Same thing with chlorine. With 17 protons, it's chlorine all day long, right? But now that we have that chlorine has taken an electron away from sodium, right? Now its electron count is down to 10, and chlorine's electron count is up 1 to 18. So you're right, they're going to be charged now. And we're kind of hopping around a little bit in the presentation set, and that's okay. But I think it kind of naturally flows into ask the next question then. Do we have a special name for those elements, those atoms that now have charge? Like if an atom is charged, it's no longer known as a typical, just a plain old atom. We give it a special name. Yeah.
An ion?
It's now an ion, right? So we have 2 ions up here. We also have like a special category for whether it's positive or negatively charged. So if you have a positively charged ion, what's the special name that we give that? It's a cation, cation. You got it. Yeah, sure. Right. sometimes people will remember this as Ca plus ion for cation. It's not cation, it's cation. Another student told me that they remember that cations are positively charged, and we'll put a plus on this guy, positively charged ion, because they like cats. Cats make them happy, and so it's positive. So cations.
Positive.
Yeah.
Positive.
Yeah, good play on words. It's positive, yes, very good. Yeah, doesn't work for me. I don't really care for cats. Sorry, not a cat lover. So, you know, they're okay. I can get my fix by visiting someone who has a cat. Like, you know, that's meow meow, okay, meow meow time, and now I go home and no more meow meow time. It's good. Now, with chlorine, though, then this would be a what? For a negatively charged ion, we call them anions. Anions, yeah. A negative ion. Yeah, it's right in the name. A negative ion. Okay, so we should be kind of understanding that, like, the form ionic compounds, we have a metal, like sodium, a non-metal, like chlorine. There's going to, the non-metal wants electrons bad. And so it's going to steal them, take them, rip them from the metal, who really is kind of indifferent to whether it keeps those outer valence or not, because it would prefer to actually let them go to achieve chemical stability. All right, so now that this has happened, what's the natural thing to happen between these two charged ions? To stick together, right? You have opposite charges right next to one another. Right? These guys have to get close enough for this transfer of the electron to happen. Okay, so sometimes students ask, when does this happen? Like, what's the order of events? The first thing that has to happen is the electron has to get moved. Right? As soon as that electron is ripped away from sodium, now it has a positive charge. This now has, once the electron enters this electron cloud, it's now negatively charged. And because this is so greedy for electrons, it's not going to share it back. Hardly ever, if at all. It kind of, sort of, technically, nerd boy would say, it kind of does. It does. It does. But so seldomly, we consider it to be taken. Right? And so you're right, these two guys are going to want to hang out together now that they're obviously charged. There's another way we can kind of show this. Instead of drawing like all those circles and everything, we can draw what's known as a Lewis dot diagram. This is where we show just the elemental symbol, and we put dots around it to show how many valence electrons it has. And you can only put up to 2 electrons in every quadrant. So you could put, like for sodium, we put its single lone electron right here in the north quadrant. North, south, east, and west, or up, down, and left, and right, whatever you want to consider it to be. All right, and then we can also then draw, we'll put chlorine up here, and same thing. It has 7 valence, so we'd say, okay, 1, 2, 3, 4, 5, 6, and I'm going to put my 7th dot over here for obvious reasons, because it's convenient to draw that this is going to get transferred, to the chlorine. Chlorine's going to take it. But these would be Lewis dot diagrams for sodium and chlorine, and it helps you kind of see what's going to happen. This guy has some open real estate, has an open spot right there, and it could really use that electron. Sodium has a lot more open spaces, so it actually would like to empty that level out. Now, once they do form these charged cations and anions, we can then also show that as well. So this would be kind of like describe or illustrating what's going to happen with the electrons. When the electron is actually transferred over and is actually part of chlorine now, we would go ahead and further note that in square brackets, this guy is now a positive cation, and this guy is now a negative anion. Right? So that would be the appropriate sketch to show that they are now charged, not that we made a mistake in our error in our math for valence electrons. And you're right, these guys are going to get cozy, and they're going to hang out, and they're going to form NaCl. So we know that this, just by looking at what is put together, you should be able to identify that this is ionic, like straight away. Just like you should be able to identify that, MgCl2 is ionic as well. Or how about CuO? And you should know this because of what's put together. I mean, look at what is being put together in each of these on the front side of these compounds, and then compare it to what's being attached to on the other side. Right? All of these have metals with nonmetals. That's the easiest way to know that's ionic. I mean, metal with nonmetal, ionic all day long. Okay, so that gets us into covalent bonding. How about that? All right, so let's think about this for a moment. Right? In covalent bonding, by definition, we're saying that a covalent bond, a connection between two atoms, is covalent if they're sharing. If they're sharing electrons. Right? So if we consider the different types of elements for like the three standard types, like metals, metalloids, and nonmetals. If we consider that idea, maybe even include the metalloids with the metals. Right? So if you're a metal or metalloid, we're going to say that you're more of a metal-like element, and then and otherwise we're going to think you're kind of more non-metal in your behavior. Right? So if we think about the setup, right? I'm going to hop back out of this and go back to our drawing board here. Okay, so we talked about when we have non-metal or metal with non-metal, so Na with Cl, all right? And we said that the electron will get taken by chlorine because chlorine is greedy for electrons. What if we were to have a couple metals hanging out? Right? What if we had like magnesium with two valence electrons hanging out with another magnesium that has, two electrons? So they're completely separate from one another. So we just take these and plop two of these individual magnesium atoms next to each other. Are they going to want to do anything bonding-wise? Are they going to want to chemically react with one another? Why or why not? And to help you, the hint is, what will they want to do with their electrons? I mean, in fact, you're right, only the valence matter. The magnesium has more than 2 electrons on it. Don't get fooled. It has 12. Each one has 12 electrons, but only 2 are on the outermost level that actually do anything chemically. Okay, so like if they're all giving things away, like who's going to pick them up? Right? I mean, if this guy's like, oh, dude, I really want to get rid of these two, and I want to get rid of these two as well, and I want to get rid of these two as well, and I don't, not necessarily that they actively want to get rid of them, but they would prefer them to be removed from them than try to find 6 more. They're not desiring more electrons. None of them are. So the odds of them doing anything chemically is slim to none. Right? They're just going to hang out. And this is why we don't have a different type of bonding for this situation. Right? We don't really have that. In fact, it's more. This would be more falling in the lines of metallic bonding, because it makes more sense that if these guys are all hanging out with one another, all these electrons will kind of like flow around everyone, because no one really wants them, but they're going to tolerate them being around. It's like when you go to the park with your parents when you're little, and then other parents have other little kids there playing as well. Your parents are okay with the other little kids hanging around them, but they're not going to take anyone home. Right? So they're going to only keep what they came with. That's it. Because 1, that's kidnapping. And 2, usually you're kind of content with what you have. It's like, we have 2 children, we're good. We don't need any more children because we learned our lesson from the second one. So that's what happens with metals with metals. So we don't see anything special happen. But let's consider then another situation. Why not consider nonmetals with nonmetals? I mean, why not? So let's do something simple, like let's do hydrogen with hydrogen. That'll be simple. Hydrogen and hydrogen. We'll keep it simple for this time around. Okay, so we have 2 nonmetals, and if you remember from the Bozeman video, they mentioned this idea of electronegativity, or EN value. Right? It's a scale from 0 to 4. 4 being the most greedy for electrons, and the one that's most greedy for electrons in the periodic table is fluorine. Fluorine is like Greedy Von Greedy. He's Blackbeard the pirate of the periodic table. He takes electrons and doesn't even care where you came from. Like he will rip electrons from even noble gases if he has to, right? He is that notorious, that vicious, that dark. Chlorine's not far behind. Chlorine's kind of like Jack Sparrow maybe or something like that. So he's more the Johnny Deppish, the kind of cool cat, you know. But fluorine's like the ultimate evil Blackbeard pirate guy. All right, so but we have two nonmetals here, and if they're both greedy for electrons, when one gets kind of close to the other one, they're going to try to maybe take and borrow an electron from the neighbor. But at the same time, the other one's also going to want to maybe commandeer one of their electrons for a little bit of time. And the idea is this. Like, if you look at like electronegativity values for hydrogen, they both have a rating of 2.2. Right? Fluorine on the far end of the scale is like 3.98. Like, the reason they didn't say 4 is because what if we find something that's a little more greedy sometime later in the future? Let's leave ourselves a little bit of wiggle room. let's not max ourselves out yet. But you could probably call it 4. So these guys, so fluorine is very, very greedy compared to these guys, and we'll look at fluorine with these two in just a moment. But let's just focus on our hydrogen. So wall between you two. If these guys both have a desire for electrons, then as they get close enough, and it's like magnets. You know, if you have magnets with opposite ends facing one another, as you have them far apart with no real pull or draw with one of them, but as you get them close enough, you start to feel that you're starting to resist their desire to kind of come together and snap together. And that's what we see happen here. There's like a sweet spot zone when we get these atoms close enough where the proton in the center, which is positively charged, by the way, right, it has an attractive pull on that electron because it's negatively charged. And likewise for the other hydrogen. And so we actually see them share those two electrons between the two of them. Right? So this bond line, or when you normally see like chemical structures kind of sketched out, this is representing a shared pair of electrons, one from each of the hydrogens. And why would they do this? Why does this work well? Well, think about it. If for a moment of moments the electrons are shifted to the leftmost hydrogen, it has a full first energy level. It has the 2 electrons that it needs, and that works. If they shift the other way for a moment of moments, then the other hydrogen is satisfied. And so these electrons are moving back and forth between these two atoms at a certain distance apart across this electron highway almost. That's what bonds these guys together. Because think about it. If the electrons are shifted towards the other hydrogen for a moment, that's going to make the rightmost hydrogen slightly negative because it has both electrons. And the one to the right is going to be slightly positive because it has, all of them, one electron it has is being shared over there. And so that's going to hold them together in place, and then it's going to want to make those electrons flow back the other direction. So this would be covalent because we're sharing electrons. Because they share them even Steven, because they both have the same desire, that 2.2 rating. Right? This would be known as nonpolar covalent. This is nonpolar covalent. Nonpolar meaning that you don't have a preferred positive or negative side of that molecule. You're okay with that. They both desire electrons equally, so it's a nonpolar covalent bond. Okay, what if we put hydrogen with fluorine? And fluorine, as we talked about, is like, it really wants electrons like super, super bad. Like bad. Alright, so let's hop the screen over for them. And let's go ahead and sketch these guys out. So we have hydrogen with its 1 electron here. We have fluorine with its 7. Okay. If we look at the electronegativity rating for both, right? 2.20 for hydrogen, 3.98 for fluorine. This is a rather large difference between their desires for electrons. And it's almost to being ionic. When the difference is big enough, then the sharing doesn't really happen. It's more of like a take. And that's what we see between metals and nonmetals. But with nonmetals and other nonmetals, it's close enough just to be shared, but in this case, it's going to be unequally shared. So you're right in saying, like, oh, look, there's a vacancy here, and actually there's a vacancy, like, for hydrogen, because it could use, like, one more to be complete. And so they're going to coordinate that between the two of them, where fluorine is probably going to end up actually hogging that one electron longer than it should. But we would still have a single bond between these two guys. We're trying to make that single bond. There we go. Okay, now, here's the thing, the take-home idea here. Because their ion differences are so much, this would be a polar covalent bond. Polar covalent. It's polar because the electrons fluorine is so greedy for that electron that we would actually write over here that it has a partial. This is the lowercase delta. Looks like a fancy D with a curvy top. But this is lowercase delta. Uppercase delta is a triangle. Most of you know that from change in or being a change of. This is lowercase delta. This just means like there's a partial charge here. Well, if electrons spend more time over here, it's a partial negative charge, right? And so it's like it's hogging electrons over this direction. That means on this side of the molecule, you would have a partial positive charge. All right, so we've looked at ionic bonding. This is close to what happens with ions, right? Ionic bonding, we have a positive negative charge first, and that's what bonds them. In covalent bonding, we're sharing electrons. And if they're not shared equally, then we see a side of the molecule that's negatively charged, where they're hogged, and a side of where it's positive, where they're not shared back as evenly as they should be, or as what we would want them to be, I suppose. All right, now here's why this kind of will tie into what we see happen with the behavior of water. Right? We take this is known as a polar molecule, right? This is hydrofluoric acid, if we wanted to really get technical about its name. This is, in my opinion, this is probably the most dangerous substance on the planet because it will react with just about anything. I believe this will even eat through like glass. It's like that, like reactive. It's like ridiculous. All right, so what if we put another hydrofluoric acid or another HF molecule near this one? How would it want to set itself up? Where would each atom or part in that molecule want to be when put close to this one? Yeah.
Like the H should be with the F, with the H.
Yeah, absolutely correct. Right. If we were to sketch in another one of these guys, and I'll do this guy in blue. Okay, he would be like the F would be on this side, and the H would be on this side. Why? Yeah, because we'd have a partial negative on this fluorine that hogs electrons, and we'd have a partial positive on this side where they don't get them back very much. Now, this is very similar to what we see happen with NaCl, wouldn't you think? I mean, if you consider that, and I'm going to hop a page here. If we have Na with a positive charge with Cl, which is a negative charge, we put that guy together, it's NaCl. If we give them chlorine's bigger than sodium atom-wise, so that's why I dropped chlorine bigger. But you know that this is going to be this will be your positively charged side, and this is going to be your negatively charged side of the ionic compound. And if you were to put more NaCl with this one, you'd be correct in saying okay, well the chlorine must go next to the sodium because it's negatively charged, and the other next sodium atom would want to be next to the chlorine because it's positively charged. And you're right. And so this is what leads to the fact that polar things will interact with other things that are polar. And in particular, like ionic compounds. If we consider to put together water, right? We have oxygen, hydrogen, and hydrogen, right? Oxygen is going to have 6, 1, 2, 3, 4, and I'll put 5 and 6 right here. Hydrogen has 1 and 1, valence-wise. So if we were to, again, think about what's going to happen to coordinate these guys to share, these unpaired electrons will get shared and will form a single bond here. These guys will also be paired up and share a bond there. And so this is your water molecule. Now consider the EN values. Hydrogen is 2.20. and water or oxygen is I think 3.14. I'll double check. 3.44. Sorry.
7872.
No, it's just 3.44. All right, so it's not pi. The oxygen is very greedy for electrons. So they're going to spend more time around the oxygen. This is going to give it a partial negative charge, partial negative charge here near the oxygen. And it's going to give you partial positive charges near the hydrogens. And so if this is, this is our solution before we put salt in it, when we put the NaCl in, right, the Na has a positive charge on it, the chloride has a negative charge on it. This guy's going to get drawn towards the negative end of water, and water actually is going to get in there and surround or hydrate, I suppose, the sodium. And then it's also going to surround the chlorine, but it's going to face its hydrogen ends towards the chlorine atoms. And that's what gets in there and separates the sodium chloride. So when sodium chloride dissolves, it actually gets dissociated in water. When the sugar gets dumped in there, there's not a preferred end to it. We really can't, probably the easiest way to show you sucrose is to use MolView. This thing is awesome. If you've never been out here to use MolView, after today you might. Sucrose. There. So this is a sucrose molecule. Yeah, pretty awesome. Pretty amazing. But the idea here is that all these different bonds, especially these chains of carbons that we have here, and the connected oxygen, the span between each carbon chain that we have, and it's not going to have a preferred end to it. Right? It's not going to have a positive charge and negative charge because it's going to be non-polar covalent. But that's why, right? So now the last thing to consider then between now and tomorrow is, what does that mean about the water molecule? That it has positive and negative charges, regions around it, and as you start to cool it and move those molecules more slowly and more slowly and more slowly as you drive heat away from it. As you go from gaseous water to liquid water to solid water. Like, what might happen with those molecules as you get it to change into solid state?